Hello, welcome to lecture 3. In this, we will do the derivation of the Reynolds transport theorem. As we mentioned in the previous lecture, Reynolds transport theorem helps us to, it's a mathematical transformation that helps us go from a systems approach to a control volume approach. So first of all, for deriving the Reynolds transport theorem, we will look at the statement of the Reynolds transport theorem. So it says time rate of change of a property which we will calling B in our derivation in the system is equal to time rate of change of B in the control volume. CV is the short form for control volume, plus net flux of uh, B through the control surface. CS is the abbreviation for control surface in this derivation. So time rate of change of a property in the system is equal to time rate of change of B in the control volume plus how much is B going out through the control surface. So control surface is the surface that that is bordering the control volume. So let us start with an property B. So let B be an extensive property. So an extensive property is something which is a property which is dependent upon the quantity of matter in the system. So we have done it in basic thermodynamics, difference between an extensive property and an intensive property. So something which does not depend on the quantity of matter, for example, specific heat, and then the density. These are intensive properties, but some quantities, for example, which depend on the quantity of matter in the system are extensive properties. For example, the total mass of the system is an extensive property, or the total heat capacity is an extensive property. So let B be an extensive property of the system. The system is moving at velocity u. Is moving with velocity u with respect to the CV. The system is moving with respect to the CV. For simplicity, let's assume the CV is stationary, the control volume is stationary. So this is just for simplification. This does not, we do not lose any signs if we assume this. This is just to make our derivations slightly easier. So this is this is system A, a system at time A, and we will so this is time t plus dt. So at time t, we had a control volume and a system which were um, in the same position. So the system is the CV is the system. There is nothing wrong in this. So uh, this so let's uh, show the system to be with these dots. So the system and the CV are coinciding at time t. So t is the reference time. This is the time at which we start our analysis. And at time t plus dt, the system now, which is this new um, uh, deformed object that you see, the system can change, of course, shape with time, but the amount of particles in the system will remain constant. So this is now the system at time t plus dt. Okay, so this is the system, this is the system. So this was the system at system was coinciding with the velocity, with the control volume at time t, and t plus dt, it has moved out with velocity u. So let's mark these variables. So so let's say this is point A, this is point D, and then let's say this point where it intersects is C, and there is a point E on the control surface. So, and the system is moving out with a velocity. So this velocity is u. So this is going out at velocity u, and u is arbitrary, so it can point in any direction as with any velocity vector. It can have 3 components. So this region, let us mark this region as 1, this region as 2, and this region as CV minus 1. Okay, so 2 is the region which is outside the control volume in this and is bounded by A and C arc, I mean point between A and C. So let me get the pointer. So this is bounded by this region. So this is 2. This is CV minus 1 because the whole is CV and we have marked this as 1. So this is CV minus 1. And we have the control surface. So these are the control surfaces. Okay, so the control surface is bounding the control volume. So now at time t, the property, extensive property of the system, so the extensive property of the system at time t is equal to BCVT, because this is what we are defining. So we have the control volume same as the control as the system. So the extensive property has to be same. So B can be is an extensive property. So this can be a scalar or a can be a scalar or a vector property. There is no limit. I mean, there's no such limitation on what B can be. At time t plus dt, we have B system t plus dt is equal to BCV t plus dt minus B1 t plus dt plus B2 t plus dt. So this is, of course, it has to happen. So system has moved out now from position 1, hence there is a negative sign here. It has filled position 2, hence there is a positive sign here. So once we have that, if we want to find out the time rate of change of the B system, this is equal to B system t plus dt minus B system t divided by dt. And this is just the time rate of change of the quantity B in the system's frame of reference. And this one, if you expand it using these two equations, equation 1 and equation 2, because you have now defined both B system t in terms of CV. So if you do that, you will have dB system dt is equal to BCV t plus dt minus B1 t plus dt plus B2 t plus dt minus BCV t. This is what follows from equation 1 and 2 on the previous slide. So this can be rearranged. So this is just a change in notation, nothing new here. BCV, you can also keep it dB system by dt, it's not a big deal. So minus BCV t, I am just rearranging. I've just as you might have seen, so might have already understood, this BCVT has been taken here, and both of these are clubbed together to make things slightly easier for us to understand. Minus B1 t plus dt by dt plus B2 t plus dt by dt. So this is a term which gives us the outflow. So this is a term that gives us the inflow. This is a term that gives us the outflow. Flow through the control surface. Okay, so we need to derive some expression for these two terms, that is term 2 and term 3 here. This is term 1, let's say. So we are deriving some expressions for term 2 and term 3 to make it slightly more generic. So to do that, let us take a surface let us take a surface like this, and let us take an area which has an infinitesimal area which has whose value is dA, and n cap is the direction which is perpendicular to the area element. So the area is a vector, and then the direction normal to the area is the n cap direction, and the velocity u comes from the previous slide. This is the velocity by which the control surface is moving out. The system is moving out of the control volume through one of the boundaries, I mean one side of the control surface. So this is vector u, and u can be arbitrary, of course. It does not that means the system is not going out perpendicularly at that location to the control surface. It is going out at a certain angle, which is fine. It is just a generic vector, so it can have any direction. So now after some time t plus dt, so at time t, so at time t we have this configuration. At time t plus dt, what happens is now there is an extruded cylinder, because now, I mean, this is an imaginary cylinder, of course. The flow has, so the velocity vector has moved, I mean, the system has moved because there is a velocity associated with the system, and it has moved a certain distance, and at this time t, I mean, in this short time dt, it has traversed a very small cylinder, an infinitesimal cylinder, along its normal direction, and velocity vector is still this u. So there's a small cylinder which has been extracted, I mean, which it's an imaginary cylinder that we that will be extruded because that will be extruded perpendicular to the surface because of the system moving out. So this is just for us to get an understanding of the flux. So this is of course an imaginary cylinder, and this direction, I mean, the length of the cylinder is dln. So ln is the length perpendicular to the n cap vector. So the cylinder is perpendicular, and dl is the length which is parallel to the u vector. So dl is parallel to u, dln is parallel to n cap. Okay, it may not, my schematic is not probably exact, but it is, this is what I mean by dln and dl. So now dl is equal to v dt. Sorry, this is u dt. This is u dt. Our velocity is measured with the vector u. This is the variable, and the distance it has, and the distance that we can get out of this velocity is u dt. However, the perpendicular distance is dln. So dln is dl, as you can see from here. Dln is equal to dl cos theta, where theta is the angle between the normal vector and the velocity vector. So moving on to the next slide. Now we have, so the infinite, so now we calculate the volume of the cylinder. Okay, so this is, let's say, the infinitesimal volume is given by d lambda. So now the infinitesimal volume of the cylinder, of the imaginary cylinder extruded perpendicular to the area element, is given by dA times dln. This is how the cylinder area is. It's the area times the length. The perpendicular length is dln. Now this is equal to dA times dl cos theta, because dln is dl cos theta by simple trigonometric relations, and this is equal to dA u dt cos theta. So this is infinitesimal volume swept in time dt. In the small time dt, this is the volume that has been swept by this swept perpendicular to the area element. So now the reason why we have been doing all these is to please remember that we need to find some expression for terms 2 and 3. So that is the reason why we are getting to we're doing all of these. Hence we are close now. So amount of element, amount of extensive property B now exiting is dB equal to B times dm equal to B rho d lambda. Now I have to define these variables, whatever I have written down. So here B is the intensive property corresponding to B, intensive property corresponding to capital B, and is equal to B by the total mass. So this is an intensive property. This should not depend on the total matter in the system. And rho is the density. This is the density of the system. If it's a fluid, I mean it could be a liquid or a gas. So this is the density. These are all generic properties of the system. So B rho dA u dt cos theta. So this is where we have derived this expression. So using this equation 3, we get have to name this equation at this point. It might be confusing later on. So B rho dA u dt, this comes from this expression that we have derived for d lambda. So once we have this, so dB by dt is equal to B rho dA u cos theta, and this is B rho dA, the magnitude of u, magnitude of n cap, cos theta. So this we can always do because magnitude of n cap is 1, so it does not make any difference to the equation. Hence this can be written as B rho dA u dot n cap. So this is how we can just rearrange the terms. We have introduced n cap here, and this is not a big deal because mod of n cap, the magnitude of n cap is 1, so it does not change anything, and of course u is mod of u. So this is u dot n cap. So once we have this one, so now flow rate through AEC, that is, so I'll go back to the diagram again. AEC is this surface, is the surface where through which the system is moving out. This is AEC, and the other one is ADC. So the flow rate through AEC is given by integral over the whole control surface u dot n cap dm. So we saw previously that the amount exiting through a very small surface, infinitesimal surface, is given by the rate of change is given by this one, this expression. Now once we have this expression, now we are getting the total amount which is going out through the whole surface, AEC. So we are integrating across the whole surface. So this is for an infinitesimal area, and this expression is now for the whole AEC through which the system is going out. Now flow rate, similarly, flow rate through ADC, this is the other surface which is actually the surface through which the system has left that surface and system is going out through the other surface, is also similarly B rho u dot n cap dA. u dot n cap would be negative. So this will take care of the fact that whether something is going in or coming out. So now net outflow, so this vector dot product will take care of the directions. So net outflow through the control surface is equal to AEC plus ADC B rho u dot n cap dA. So this is AEC plus ADC is the control surface. If I again go back to the diagram, AEC plus ADC is the control surface. These are the two arcs. So this is, hence I have written this as a control surface here, and B rho u dot n cap dA. So this is an expression for the term which is for something expression for the inflow and the outflow. Okay, so this is AEC plus ADC is the control surface. So now deriving an expression for the first term, so we had three terms in the statement of the Reynolds transport theorem. So this is the first term was B dot CV. So B dot CV is equal to d dt integral over the control volume of this quantity B. So I'll go back again in the slides to see. Yes, so this is B dot CV. We are trying to find an expression for this first term, B dot CV. So B dot CV is the time rate of change of this infinitesimal quantity B, but integrated over the whole control volume. So this is equal to so this is integral. So dB is of course B rho d lambda. D lambda is infinitesimal volume, and we can take the time derivative inside the integral, assuming that this quantity, this the partial derivative of b rho times dt, b rho partial derivative of b rho with respect to time exists, and the function is continuous, and the CV is not deforming. Okay, the CV is stationary. That is, the limits of the integration are constant. In this case, we can take this inside. So from this equation and the previous equation, we get to the final form of the Reynolds transport theorem. So we have dB system by dt, which we have also written down as B dot system, and just a different form of this same thing. So this is the final form of the Reynolds transport theorem. Now this comes from this equation 2 and this previous equation 1. So 1 plus 2, you will get this final form, this Reynolds transport theorem. So this gives us the, so this is the rate of change of B with respect rate of change of B with respect to the system rate of change of B with respect to the control volume and the net flow through the control surface. And this is what the original statement of the Reynolds transport theorem is. So something which is changing, so we have derived the change of a quantity with respect to the system with respect to the change in the with respect to change when we assume a control volume approach.